Alright, class, welcome back from Easter break. Hope everyone had an enjoyable, restful time. What we're going to be doing today is covering the last little bit of information we have in Unit 7 in preparation for a test later this week on Thursday. So the bulk of this lesson is going to be focused in on intermolecular forces. Before we get that, we're going to build upon our discussion of polar covalent bonds that we did before we left for Easter. So we know that some of our bonds can be characterized as either polar or nonpolar depending upon the elements that make up the two atoms in those bonds. But the same thing can apply to molecules as well. So you look at molecules as a whole, some of them that contain polar bonds are also going to be polar themselves. The entire molecule itself is polar. So what this means is in these particular types of molecules, one end is going to be slightly negative, while the opposite end is going to be slightly positive. So just as we had this positive negative end of a bond, we're now applying it to the entire molecule as well. So what we have is that these electrically charged regions, in this case either slightly negative or slightly positive, we're going to call these regions our poles. So our dipole is going to be a particular molecule where we have just two poles. So again, that prefix di just represents two. We're going to have two poles in the dipole. The example we're going to be looking at is hydrogen chloride. So before we looked at this polar bond between hydrogen and chlorine, again, because hydrogen has a very low electronegativity, chlorine is going to have a very high electronegativity. And because of this difference between low electronegativity and high electronegativity, there's going to be a polar bond. Because this is the only bond at play here, the entire molecule itself is also going to be polar, creating this dipole. So if you look at our hydrogen atom that's within this compound, our chlorine is going to be much larger than our hydrogen. Hydrogen is made up of just one proton, one electron. But due to the low electronegativity of our hydrogen, what we're going to have is hydrogen is going to be an overall positive charge because it's going to have its electrons taken from it and it'll be moved closer to our chlorine. And because chlorine is highly electronegative, it's going to want to bring the electrons closer to itself. It's going to have this partial negative charge. So the molecule itself, hydrogen chloride, it's going to be polar. It's going to have a slightly positive end, or our positive pole is going to be by our hydrogen, whereas our negative pole is going to be the side of the chlorine. So all we're doing is applying this idea of kind of a polar bond to now we have a polar molecule as a whole. So when we look at all of these molecules we've been studying so far, is that they're going to have a few different atoms that are going to be held together by covalent bonds. So if we look inside of a molecule, what we have is a couple of different atoms going to be held together by covalent bonds. We refer to these covalent bonds as intramolecular forces. So when you say intra, we kind of mean inside of. We're looking at these forces that occur within a molecule. But we also have an additional type of force we're going to call intermolecular forces. So when we're looking at groupings of molecules as a whole, these grouping individual molecules can also be attracted to each other through these things we're going to call intermolecular forces. That prefix inter is going to refer to between molecules. So the way we can remember intra versus inter, right, if we think about, say, like an interstate highway, so a highway such as I-95, that connects Maryland to Virginia and many of the other states along the East Coast. Our interstate highway connects multiple states. The same way that our intermolecular forces are what are going to allow individual molecules to be attracted to each other. So the reason why our intermolecular forces, also called intermolecular attractions in your textbook, are important is because they give rise to many of our properties we'll look at. One thing we know about these intermolecular forces is that they're going to be much weaker forces than our ionic and covalent bonds we studied previously. How strong these intermolecular forces are going to determine the physical state of a molecule, so whether or not it's a gas, liquid, or solid. What we see is that if the intermolecular force is weak, we're going to have the result will be a gas. So our weakest intermolecular force, I'm going to abbreviate here as IMF, will result in gases. As those intermolecular forces get stronger and stronger, then we're going to go from gas, we might create a liquid molecule instead, such as water, or eventually we might have a solid molecule, such as a diamond, which is made out of carbon molecules. Again, so our solids are going to be held together by these the strongest of our intermolecular forces. So again, we're going to have intermolecular forces that are weak will result in gases. The stronger we get, closer we'll get to being a solid. What we have is in our molecular compounds, we have this large diversity of physical properties. Molecular compounds include everything from the oxygen gas we breathe in, to water, to diamond substances, to coal, to glucose sugar. We have this very vast array of many different types of compounds. This large diversity of their properties can be the result of these intermolecular forces. So looking at specific examples of intermolecular forces, very first type is we're going to be focusing on are called van der Waals forces. A van der Waals force is just a large name for two different types of molecular forces. So these two types are going to be dipole-dipole interactions. Our textbook refers to them just as dipole interactions. Second type is going to be London dispersion forces. Again, our textbook simplifies it down to just dispersion forces. But these van der Waals forces, these two we have listed here, are going to be the weakest of our intermolecular forces of this attraction between molecules. Looking at that first type, our dipole-dipole interactions, when we compare the two van der Waals, these are going to be the stronger of the two. And that opening slide of today's class focuses in on polar molecules. And these polar molecules will be very important to these dipole-dipole interactions. So this type of interaction only takes place with polar molecules. We're never going to see this with nonpolar molecules. And what we have is that a slightly negative pole of one molecule is going to be attracted fairly weakly to the opposite slightly positive pole of another molecule. So if we look at just these two molecules here that we have circled, in green we're going to have that slightly positive pole, and it's going to be attracted to the slightly negative pole of a second molecule. So again, anytime we have a positive and negative, we're going to have this force of attraction we see here along this dotted line. But this force of attraction can be fairly weak. It's going to be much, much weaker than, say, the force of attraction between our positive ion and a negative ion in this ionic bond. Our second type of van der Waals forces is going to be our London dispersion forces. And this is going to be much weaker than our dipole-dipole interactions. And this can take place between all molecules. So dipole-dipole is only for polar molecules, but London dispersion forces also work for nonpolar molecules as well. So what we actually have is a very similar process in the fact that we're going to have this force of attraction between a positive charged area and a negative charged area. But what we have is when we think back to the movement of electrons in atoms, this movement of electrons is going to create what we're going to call a momentary or a temporary dipole. So what happens is as these electrons move around the atom, at some point through this random motion, we're going to have a majority of our electrons are all going to collect on one side of a molecule. So what we're doing is we're kind of creating this momentary or temporary dipole. So for a split second, most electrons are on one side, giving that an overall negative charge. That slightly negative partial charge we have on one side is going to be attracted to another molecule. So very similar to this dipole-dipole interaction, it's going to be a lot weaker though. We're going to have this, what we call kind of an induced, this temporarily created dipole. It's going to happen just for a split second and then vanishes as our electrons move away. But we still have a little bit of a force of attraction between even these nonpolar molecules. And what we have is that the strength of this force is going to increase as the number of electrons in a molecule increases. So the more electrons we have, the stronger this temporary dipole is going to be, the stronger London dispersion force will be. Our very last type of intermolecular forces are going to be our hydrogen bonds. This is going to be the strongest out of all of these intermolecular forces we'll cover for today. And what we have is our molecules are going to have to contain hydrogen atoms covalently bonded to a very electronegative atom. This is going to result in a very polar molecule. So if we think back, hydrogen is going to have a very small electronegativity. And if something with a small electronegativity is bonded to something that has a high electronegativity, it's going to create a polar bond. So the example of this is water, H2O. The most common hydrogen bond we study in chemistry is found in water. Again, because water is very electronegative, we're going to be able to have this hydrogen bond. So we have the hydrogen atom, because it has a small electronegativity, it's going to become slightly positive. So the hydrogen will form a slightly positive pole. And as we can see down below here in our representation of our water molecule, what we have in gray are going to be our hydrogens. In red is going to be our oxygen atom in H2O. So our hydrogen is going to have this slight positive charge we can see here, whereas our highly electronegative oxygen is going to have a slightly negative pole, which we can see again right here, that negative sign we have next to our delta. So we have positive pole in one atom, or one molecule, is going to be attracted to the negative pole in another, and it's going to create this hydrogen bond between them. So this process is similar to dipole-dipole in that we have a negative pole is going to be attracted to a positive pole. But in this case, because we're dealing with very polar molecules, it's going to be a much stronger interaction. So guys, this concludes our information for Unit 7. Just a quick note about the rest of the week. Again, we're going to have a conference call tomorrow during our normal 8-day scheduled class. And this conference call is mandatory. Attendance will be taken for the conference call. And we're going to go over and review the material we saw before break, just as a refresher for you all, since it might have been a while since we looked at that material. So note about our test is it will be open note. So all the notes you've been taking through these videos, through your reading assignments, homeworks, previous few weeks here, you can use on the test. The way the test will be conducted is it's not going to be a Canvas quiz. Instead, you're going to be sent a PDF of the test as assignment through Canvas, just as we would say like a problem set. You're going to open up Notability. The big thing is that you must handwrite all of your responses. So nothing can be typed, it all has to be handwritten, just like you would if you're taking a normal test in person. And when we think about the topics, right, everything we've done in Unit 7, going all the way back to the beginning, we talked about covalent bonds and how they will form molecules. We compared the different properties between molecular compounds and ionic compounds. We looked at the difference between structural formulas and molecular formulas. Then we figured out how we could actually create and draw these structural formulas, beginning first with single bonds, then expanded to double, triple bonds. And from there, we added in our polyatomic ions, which are ions that are made out of small groups of atoms that are covalently bonded to each other. Lastly, the information you did over Easter break included bond types, determining if something was going to be a polar bond or a non-polar covalent bond. Last thing we have for today was our intermolecular forces. So these are going to be all the topics for our test on Thursday. And if you have any questions on the material in this video, any other questions from previous in the unit, please let me know. I'll be happy to help.